Now next we'll move to the next topic, which is law of mass action. The next topic which we are going to discuss today is law of mass action. Now what this law is, let's try to understand the statement of this law first, then I'll explain all the points. Achha, one important point about this is that this law was given by Goldberg and Walkie. This point is important. This law was given by Goldberg and Walkie, and the statement of this law is it states that the rate of any chemical reaction is directly proportional. The rate of any chemical reaction is directly proportional to the product of active mass of reactants raised to the power equal to their stoichiometric coefficient. So before understanding this law, you should be clear with one term. That what actually is active mass. This point should be cleared. Then only we'll be able to proceed in this law of mass action. So let's try to understand the meaning of active mass. So active mass is nothing but the concentration of the species. Active mass is nothing but the concentration of a species, and it is represented in terms of mole per liter. We have seen before also that concentration is also represented in terms of mole per liter. So active mass is also represented in terms of mole per liter. Only difference is that if I'm considering the concentration, we will define it for solid, liquid and gas. But active mass is only checked for gaseous system. For solids and pure liquids, we say it is equal to 1. For solids and pure liquids, active mass is 1. Or basically what we can say, that we have taken it as 1 for our convenience. Actually, the concept of active mass is like this. Active mass is written in terms of mole by volume of solution in liters, or volume in liters. And what we know, that mole is nothing but weight upon molar mass. So we can write it as weight divided by molar mass of the species into volume of the species in liters. And what we know, weight upon volume, that is equal to what? That is equal to density. So this will become density. Generally we represent density by rho. So density upon molar mass is the active mass of the species. Now let's try to understand what will happen if I'm having solids, what will happen if I'm having liquids, and what will happen if I'm having gas. So let us suppose we're having two containers. First one is having volume V1, and second one is having volume V2, and V1 is not equal to V2. That one should be clear. Now what we are taking a solid block in this. Whose mass I'm assuming as m, and the volume which is occupied by this solid block, let us suppose, is V. So if mass is m, volume is V, its density, that will be equal to what? M by V, right? And if the same block is placed in this container, still its density will be what? M by V, means the density of solid is not changing. Its molar mass, that will also not change. So if density and molar mass are constant, what we can say, that active mass of solid will be what? Active mass of solid will be constant. The active mass of solid will be constant. So let us suppose I'm in place of solid, I'm taking liquid in this container. I'm taking liquid in this container. Suppose we are not having solid, we are having liquid only, whose mass is m and volume occupied by that liquid is v. So in that case, its density will be what? M by v. And if the same mass of liquid is taken in second container, in that case what we can say, the density will still be m by v, because mass and volume of the liquid will not change. And if density is not changing, means active mass will not change, and that is why we'll write that active mass of pure liquid will be constant. Clear? But if I'm having gas in this, let us suppose in this container we're having gas with mass is equal to m, then volume occupied by this gas will be what? It will be equal to the volume of the container, which is v1. So in this case, density of gas will be equal to what? M upon v1. And if the same mass of gas is taken in this container, let us suppose we're having gas whose mass is m. Now in this case, the volume which will be occupied by this gas will be what? V2. And if volume occupied by gas is V2, its density will become what? M upon V2. Now what we can observe, that density of gas in the two containers, it is what? It is different. And if density is different, means active mass of gas will be what? That will be different. So this is the reason that why we calculate active mass for gases, and for solids and liquids we say it is constant, and that constant is taken as 1. This point is clear or not? So this much is an active mass. Let us suppose we're having a question like this, that calculate the active mass of A, 28 gram nitrogen present in 1.5 liter container, and second will be 100 gram calcium carbonate present in 2 liter container. Now what we know, that active mass is moles upon volume. Active mass is moles upon volume in liters. Now for the first question, what we can say, that moles of nitrogen, that will be equal to what? Its mass upon molar mass. Mass of nitrogen is 28 upon molar mass of nitrogen, that is also 28, means moles of nitrogen present is 1. So active mass will be equal to moles upon volume, which is 1 upon 1.5. So this will be the active mass of 28 gram of nitrogen present in 1.5 liter container. But why, if I'm having second condition, that if I'm having 100 gram of calcium carbonate present in 2 liter container, so in this question we don't need to find anything, because what we know, that calcium carbonate which we are having, that is in solid state. And if it is solid, if calcium carbonate which are taking is solid, its active mass, that will be equal to what? Active mass will be written as 1. So you have to keep in mind whether the given species is in solid state or it is in gaseous state. Now you're clear with the concept of active mass. Now let's back to law of mass action. Now what does it say? That the rate of any chemical reaction is directly proportional to the product of active mass of reactants raised to the power equal to their stoichiometric coefficient. Means if I'm having, for example, if I'm having a reaction like this, AA plus B B is giving you Cc plus Dd. So if I want to find the rate, so according to law of mass action, rate is proportional to concentration of A raised to the power capital A into concentration of B raised to the power small b. Again I am repeating, rate is proportional to concentration of A raised to the power small a into concentration of B raised to the power small b, because A and B only are the reactants which we are having in this reaction. And if we want to remove this proportionality sign, we'll need one constant, so we'll write that constant is equal to K. So rate is equal to K into concentration of A raised to the power A into concentration of B raised to the power B. And this K which we are getting here, that is known as rate constant. This K over here is known as rate constant, or it is also known as velocity constant. This K is known as rate constant or is known as velocity constant. So this is our law of mass action. Now let's try to apply this law of mass action to a reversible reaction. Means if I'm having the same reaction, AA plus BB is giving you Cc plus Dd, but now this reaction is a reversible reaction. Means this part, when A and B are combining to give C and D, that will be our forward reaction, and the rate will be known as RF, which is rate for forward reaction. And if C and D are combining to give you A and B, that will be written as RB, which is rate for backward reaction. And now we'll try to apply law of mass action. We'll try to apply law of mass action to this reversible reaction. So we can write RF, that is rate of forward reaction, will be Kf, that is rate constant for forward reaction, into concentration of A raised to the power A into concentration of B raised to the power B, because A and B are only the reactants in the forward reaction. And if I'm considering the rate of backward reaction, that will be equal to Kb into concentration of C raised to the power C into concentration of D raised to the power D, because when we are talking about backward reaction, C and D will behave as the reactants. Now this Kf and Kb are what? So Kf is the rate constant for forward reaction, and Kb is what? Kb is the rate constant for the backward reaction. And we have studied that at equilibrium what happens? At equilibrium, both the opposing forces has to be equal. Means Rf has to be equal to Rb. At equilibrium, rate of forward reaction will be equal to rate of backward reaction. And if I'm writing this, it will become Kf into concentration of A raised to the power A into concentration of B raised to the power B is equal to Kb into concentration of C raised to the power C into concentration of D raised to the power D. Now if I rearrange this, if I'm rearranging this, we'll get that Kf upon Kb, that is equal to concentration of C raised to the power C into concentration of D raised to the power D upon concentration of A to the power A into concentration of B to the power B. And this ratio of Kf upon Kb, this ratio of Kf and Kb, that is known as Keq, that is our equilibrium constant. This Keq is our equilibrium constant. Is this point clear or not? And one very important point which you have to keep in mind, that this concentration of C, concentration of D, concentration of A and concentration of B which we are considering, that is the equilibrium concentration. The concentration of A and B and C and D which we are considering, that is equilibrium concentration.